Hi, everybody. Good afternoon, good morning, or good evening, wherever you are. I'm so glad to be with you here today to talk about the crystallinity. My name is Amin Zami, and I was working on this technology for more than 8 years. It was back in 2016, and it was started from the European project. And the we did the project on the automated fiber placement and the composites, and we realized that there was a lack of knowledge and lack of tools on this technology. So that's why we decided to make tools for this technology and to help other researchers and also engineers to improve this technology better and faster. Uh, in the previous webinars, we talked about some thermal and optical analysis. And today we would like to have a look at the crystallinity predictions within OTOM software. For today's example, we have presentations and we will have a look at the two examples in the software to see how the crystallinity will be predicted. So without further ado, let's share the screen and I will show you how everything works. So I hope that you will see my screen. If not, please write it down and let me know to fix it. In case of if you have any question or comment during this webinar, please feel free to write it down so I could answer these questions immediately and during this webinar. So the content of today would be about what are the AFP and OTOM and what are the crystallinity prediction for the ring manufacturing, and then we'll have a look at the Q&A if there is any question remained at the end of this session. For those who are not familiar with the automated fire placement or OTOM, I give you a very brief introductions of this. We talk about this in the previous webinars regarding a temperature analysis and the optical analysis. But here again, for those who are joining for the first time and are not familiar with this technology, let's have a look at this technology and OTOM. So basically for manufacturing the product like a fuselage for an airplane or pressure vessels, you use some sort of lightweight composites, and it is sort of additive manufacturing process. So you put the fiber reinforced layers on top of each other and make such a shapes like this. So these are the picture from the different industry and companies. And basically the ideas behind this is based on the heating these thermoplastic tapes with a sort of heating source, usually laser, and we will consolidate these thermoplastic tapes with the consolidation roller, and we make such a product like could be any sort of structure. And you will see here the main elements of this, including tape or roller or laser substrate and the knee point temperature, which is very critical. So basically, the idea is that the energy is transferred to the material, where we have a webinar on that, how the energy is transferred on optical analysis. And then this makes a temperature. We also had a webinar on this, and today we will have a look at the quality prediction, and basically we will have a look at the crystallizations, because the crystallizations will determine the how ductile or brittle material could be, or the some sort of physical property like a crash resistance, etc. So for those who are not familiar with the crystallinity, I give you a brief introductions and the knowledge for this. So for the composite manufacturing, the crystallinity is not only about molecular structure, but also how the processing conditions are look like. So if you have a goes to the higher than a melting temperature, or if you let the material cool down during the glass transition temperature, so you could have a different structure and material property at the end. And for the semi-crystalline material like PEEK and PAK, which is widely used in the aerospace structure, um, it affects this crystallinity very much. And we could say that it has a important factors for the impact resistance of those material. So basically, we have a different chain for the polymers, and if we crystallize the material, these chain are connected to each other. So if you have a more crystallization, means that more of this chain will be connected to each other, and basically means that if the crystalline phase will be more, we have a more stiffness, so increased stiffness. And if we have a more amorphous phase, we have a more possibility for absorbing the impact energy. So basically we could predict this for the processing conditions based on the thermal history of the material, and also the Avrami constant or Avrami formulation, which is well-known modeling and approach in the literature. So it's the constant, the Avrami values will be based on the experimental measurement, based on DSC analysis. And if you have these two elements, like thermal history and this parameter for the Avrami, you could expect to be able to predict the crystallinity. And it helps you to describe the kinetics of the crystallizations process and the solid state transformation and nucleation and growth phenomena. It might seem complex and a little bit not so easy, but basically we give the model the thermal history and some parameters, and we get one value, which is the crystallinity ratio, and which gives us, for example, how ductile or brittle material could be, and some other predictions based on the physical properties. So I hope that until now it becomes a little bit clear what is the AFP used for, what are the benefits, and how the crystallinity could affect the quality in the automated fiber placement and also composites, and how important it is, and how could we predict this value. So how does it work in OTOM software? So we basically have two main phenomena, which is the crystallization evolutions and the melting crystallizations. So basically, crystallization evolutions is from point A to B. So when we heated the material or around the region of the glass transition and melting temperature, and we have a melting crystallizations uh, between B to C. Here you see B to C. Sometimes the crystallization will be melted completely, like here on the top side of this figure, or could be the partially the crystallization will be melted, like B to C here. And it all depends on the temperature and also the time required to this phenomena to be happen. So if we would be interested to have a look at this literature, yeah, this is the reference. You could have a look, the formulations on this literature, and also for the evolution of crystallization or melting. And we implemented these models into the software, OTOM AFP Viewer, which is the utility software connected to the main software, OTOM AFP Engine, to do some post-processing of the data and also prediction of the crystallinity. And what we add here is the parameters of the Avrami equations, like nucleation rate constant, activation energy, and etc. Other parameters which you could get this information from the DSC analysis. For the peak material, this data is available, and also for other materials like a well-known material which is used widely in the industry, but you could change it for the other material as well. If you have a PAK or PA12 or PA6, you could add those informations here and get a different result based on the your data and material. So until now, we showed the automated fiber placement, how the crystallization is important, and how the OTOM crystallization model works based on the crystallization evolution and melting of them. So for today's webinar, I would like to show you two examples for the ring manufacturing simulation for 9 layers. So we have the example here. So the roller paths go through this movement round for 9 times, and these 9 layers will be on top of each other. And we performed already the optical thermal simulation with the main software here, and we extract and generate the thermal history of this model. So one time we use the base tooling at the room temperature, 20 degrees Celsius. This main structure is the round one, which is a thick. And one time we fix the base tooling at 140 degrees Celsius to see the differences. And we will have a look at the temperature history, material constant, and we have a look at the predicted crystallinity. So without further ado, let's jump into the comparison between the crystallization of these two cases. So these are the example. At the left side, you will see the ring with the base temperature of the 20 degrees Celsius. And on the right side, you will see the base tooling temperature of the 140 degrees Celsius, which is fixed. If I move the slider, you will see the progress of this laying up of this structure. I could also click on play, and you will see the progress of the temperature and evolutions here. And also for the right side, if I click on play, you will see the evolution of temperature. So there would be 9 layers of the thermoplastic tape would be on top of each other. And to see the layers, you could also go to the zone and exploded scene, and you will see all of these layers which is being built. And also for the other side, you could also do the same. Go to the zone to see all of the 9 layers. So these are very thin 9 layers which all would be on top of each other. So you will see this is the main structure that we have, and these are the objects that we have. We have 2 tooling, one thick layers, and like this one. This is a thick layers of the which is fixed at the 140 degrees Celsius, and this is the ones which is at 20 degrees Celsius. So let's have a look at the crystallinity of the second tooling, which is this layer. And again, we do it also here the same. Yeah. So you will see how the progress of this crystallinity look like. For the constant of the crystallinity, you could go here and look at here, crystallinity of Raman constant, and you will see that parameters here, nucleation growth, etc. You could change it based on your material, and yeah, the values like melting temperature or glass transitions. But here, this default value is for a peak material, so we don't change anything here. We go again back to the plot. We select this one point somewhere in the middle here, and click on the time series plot. Here we go, we have it. And also for the right side, we again do the same. We click one point somewhere here in the middle, and we click on OK, time series plot. So this is a temperature at this point specifically. So it's basically started from the 20 degree for the left side, go to around 200, and again damping around like 70 degrees Celsius. And for the right side, we have until around 280 and damping around 165. For your information, the glass transition here is around 140, and the melting is around 340. So for the crystallization prediction, you could click on this animation icon, which shows the crystallinity. If you hover the mouse here, you will see the crystallinity. If you click on it, it will tell you what is the initial crystallizations. You could say that you would like to see the progress only, so you put it as a 0 and the time step of the process. So it's basically automatically what time step it was used for the analysis, but you could change it also to see it for the different process times. So click on OK, and you will see that here is almost, we have got almost so close to 0 crystallinity. And for the right side, we got somewhere like this, which is 0.02, which is also very close to 0. And the reason is that because we were just for a very small time above the glass transitions temperature. Here also we were a little bit more time above the glass transition temperature. So that's why the material did not have so much time for the crystallinity. How about if we change the time step to the higher time step, like 0.2? Imagine that our process takes more time, but we keep the temperature profile history like this one with compensation in the temperature power. So we again got this very close to the 0. And how about the right side using the 140 degrees Celsius? Again, we got a little bit more, like around 0.12 as a fraction of the crystallinity. So this is for this layer, which does not go close to the melting point, so the material is not so much liquid to give the time for the crystallinity evolutions. And how about the other layers? If we go to other layers, for example, if we go to the other objects, I choose this one, tape 1. And for the other side again, click on plot, and again select one point somewhere here and click on the temperature history. And again, we do it here, click some points here, click on temperature history. So for these points, we got the temperature almost until 500, and again here 500. But here, for the case that we have a 20 degree as a base tooling, we got a damping around like 110, you see. And for this one, which is 140 degrees Celsius, we got a damping around like 190 degrees Celsius. And how about the temperature, crystallinity? Okay, if we assume that the initial crystallinity is 1, is like fully crystalline material, so we got the melting, and again we ended up is very close to 0, 0.02. And how about the right side? Okay, we got something more like 0.12. You see the reason is because we are more closer to the regions between the glass transition and melting. So we are more close to here, but at the left side, we are most of the time here, we are below the glass transition. So there is less time for the material to reach any crystallinity. So how about if we change the time step? So we change this one to 0.2. and we got something like that, 0.06 as a crystallinity. And if we change it again, like 0.02, we got crystallinity like 0.4. So almost less than 10 times more than this case. See? So at the end of the process, we got almost 0.42. Here we got 0.063 as a crystallinity. So it becomes more interesting now. This is tape 1 and tape 1. But how about the next tapes, ply tapes, so like tape 2, 3? Is it the crystallinity evolution would be like this one or not? So this is a question that we will have a look at this here. So we will close this window. Again, we go to the object, we select, we skip tape 2 because it takes more time to check all of this in this webinar. So we only check tape 3. Again, we come here, check on tape 3, go to the plot, and select 1 point somewhere in the middle, which is almost comparable locations. And we click on plot. Here we go. And here we click on plot. Here we go. Yeah. So again, the differences, we had a little bit higher temperature at the right side for the fixed tooling of the 140 degrees Celsius. And we got a slightly lower temperature. We click on these animations for predicting the crystallinity. And let's have a look. Here we got somewhere near 0.1 as a crystallinity. And here we got for the right side somewhere 0.4. So almost 4 or 5 times here we got more crystallinity based on the fixed tooling of the 140 degrees Celsius. And the reason again is because we are very close to the middle range temperature. So between the glass transitions and the melting temperature, here we are very close to the glass transition. So our material is more solid. So there would be less room and time for crystallization. So that's why we got here more crystallinity. And how about that if we change the time step? So imagine that our process time takes a little bit longer. So we got here for the left side, having the room temperature like 0.3. And for the right side, if we change the value to 0.2, okay, this is interesting. We almost got a fully crystalline material like 0.9 at the end of the process. And here we got 0.3. So for this example here, if we got a little bit higher time step, we almost got a fully crystalline material at the end of the process. So, and the reason is that we are very close to the middle between the glass transitions and the melting temperature. And here we are at this region, which is more close to the glass transition and more solid state. So this was tape 3. And let's have a look at the next tape, which is I skip tape 4, go to the tape 5, go to the object and select tape 5 and click on plot. Click on plot and select 1 point here. And again, for the other side, select 1 point here. Okay, here we go. So the temperature here again comes a little bit higher, very close to the melting temperature here all the time. We will have a look at the crystallinity. Okay, for the left side, having the room temperature we got here until around like 0.27. And for the right side, we got also somewhere around like 0.22 as the crystalline, so are very close with each other. So this is very interesting, and the reason is that yeah, because the the temperature history are almost very close to each other, and we are in the region that based on the Avrami equations that we got a similar crystallinity here at tape 5. So, did you notice this? If you go higher layers, ply tape, so it becomes more close to each other. But how about the next layer? But before going to the next layer, let's have a look at if we change the time step. So I close this one. I change the time step to 0.2. Okay, we got until 0.7, and here for the case of the fixed 140 degrees Celsius, we got almost also very close to the 0.7. So a very comparable level of crystallinity here for these two example. So this is for tape 5. How about if you go to the next tape, which I go to the tape 7, I skip tape 6, and again go to the object, tape 7, plot, tape 7, plot. Select one point here, click on time series plot. We got something like that. And for the other side, we also select one point here, almost comparable. So we got something like that. So if you had to look at these two temperature, you will see that for the right side, which is base tooling of the 140 degrees Celsius, we are almost very close to the melting and very close to the liquid phase, which is 340 degrees Celsius. And in the liquid phase, yeah, the material is starting the crystallization, and probably there would not be so much time to crystallization growth here. So we will have a look here. Here for the left side, we got around 0.17. For the right side, we got almost zero. Yeah, we got almost zero because we are very close to the liquid phase. And how about if we change the time steps? I'm closing these two. I change the time step to 0.2. Here we go. Here we got almost 0.6. And for the other side, if we change it to 0.2, we got again almost very close to the zero. And if you notice this here, we had a little bit crystallization here at this point around a time of 400, and again we remelt the material and then became close to the zero, the material crystallinity. This is very important factor, especially for the automated fiber placement, because in this process we remelt the material several times. We melt and remelt the material, and we cool down, cool the material again. So this phenomena of the cooling and melting happening many times, and melting, remelting, cooling, it brings a more complexity toward the crystallization evolutions and also crystallization melting. This becomes a little bit more complex for the more complex geometry, more complex layup, and also larger shapes. And it becomes more critical to know that which part of the structure is more brittle, which part of the structure is more ductile, which part we could expect that we could have a more crash resistance, or the problem with the crash that could emerge. So this all of these informations helps a designer to to understand and fix and improve the design faster before doing any experimental work. Give a little bit knowledge, general informations to know that what is my design expected to be. And this, at the end of the day, helps the either engineers to improve their designs and quickly go into the productions with the right choices, and also for the researchers to find and answer their research questions. So how about if we have a different geometries, material, you know, all of this complexity brings a different scenario for the predictions of this crystallinity phenomena. So I guess for now that was the crystallinity predictions in OTOM software. If you have any question or comment, please write it down and I will answer your question or comment. And if you are interested to check it yourself, you could go to the website otomcomposite.eu and request a demo of the software or request a private demo or download the software and check it yourself if it would be helpful for you. And I will stay for almost a minute to see that if there would be any question or comment, then I will answer those. If this webinar was a little bit fast or you missed some part of the webinar, it will be uploaded in the YouTube channel, so you could see it again if any part was fast or any part was missing during this webinar. You could rewatch this again either in the LinkedIn page or also will be uploaded in the YouTube channel of OTOM Composite. And you could also ask your questions there. And if there would be any comment or questions, we will be happy to answer those. So I guess that we are over the time by 3 minutes. And I guess that I don't see comment or question for now. So I would like to conclude this webinar and meeting. I would like to thank you, all of you, for joining this webinar, and I wish you a very good day. Thank you very much. Bye-bye.